Hello everyone, welcome to CSCN 503, Introduction to Communication Networks. Uh, this is Dr. Amr Mogi. In our last lecture, we discussed the topic of network performance. We discussed different metrics that we can use to evaluate the performance of a network, in particular delay, packet loss, and throughput. And we discussed how these metrics are related to each other and how they are calculated. Okay. Um, we are going to start the discussion today with a new topic, and the topic is actually of very high importance. It's the topic of the protocol layers. If you understand how the protocol layers work, you will be able to actually connect all the concepts and all the ideas in this course, and you will be able to understand networks well. If you don't understand protocol layers well, then you will never actually be able to get the full picture or the high level picture of how networks actually work. So protocol layers is actually one of the most important topics in networks, and it is basically how the course is going to be structured in the following lecture. To understand what are protocol layers, basically the idea is we have so many protocols in the internet, as you may expect, because we have so many devices, we have many functionalities, we have applications, we have routers that forward the data, we have systems that figure out a path from source to destination. We have so many functions in any network that require a large set of protocols to actually perform the functionality, so that at the end of the day, you'll be able to send a packet of data from anywhere in the world to anywhere else. So how are these protocols organized? Are they just actually a set of protocols, sort of like a set of programs that are plugged in and they're used simultaneously, or do they have a particular structure? They actually have a particular structure, and this structure is called the protocol stack. Basically, the protocols are grouped into layers, and the layers make up the protocol stack. Each layer is responsible for a particular functionality, and the protocols in that layer execute this functionality. For example, you have a layer responsible for the applications. It is the one that generates and consumes the user data. So when you send, for example, an HTTP request, it is generated in an application. Okay, so there is an application layer protocol that is responsible for how an HTTP request is sent. And then when the HTTP request is received at its destination, the application layer at the other end is responsible for how to interpret this packet according to the same application layer protocol. Okay. The other functionalities in the internet are supported also by other layers, and these layers contain other protocols. To understand what exactly are these layers and what are the protocols, we'll take an example. Let us say we have a company that has two branches. Okay. These two branches are located on the opposite side of the world, for example. In each building, at the top floor, you have your employees. Okay. These employees would actually like to send and receive letters to the employees at the other building. Okay, so the top floor at each of the building has people who are actually sending and receiving letters to each other. Forget actually about the internet. We're actually talking about letters that you write by hand and you put them in the envelope and you send them through the post office. Okay, so each employee is going to write the letter, and then they're going to give the letter to the floor below it, which has a secretary. The responsibility of the secretary is to take the letter, put it in an envelope, and write on the envelope the name of the person who has written the letter and the name of the person who will receive the letter at the other building. Let's call this building 1, and we call this building 2. So at building 2, there is also a floor that has another secretary whose job is to receive the letter, read the name of the person who will receive this letter, and then give it to them. Okay, so the secretary in building 2 can only do their job if the data has been written by the secretary in building 1. The secretary in building 1 must actually write the name of the person who wrote the letter and the name of the person who will receive the letter, so that the secretary in building 2 can receive this information and then they can actually give the letter to the right person. Okay. So after the secretary in building 1 receives the letter from the employee and writes the name of the sender and the receiver on actually the envelope, what do? They give it to someone in the lower floor who is responsible for all the post of that building. Okay. This person in building 1, what do? They take this envelope that already has the names of the employees and put it even in another envelope. This outer envelope will actually have the address of building 1 and the address of building 2. Okay. So here, one person is going to take the envelope that has been made by the secretary that has the names of the employees but doesn't have the address of the buildings yet. The person in the postal department will actually take this envelope, put it in even other envelope, and write on it the address of building 1 and the address of building 2. Now, the same department in building 2, someone is going to receive this letter, make sure that it is actually intended to the right address. So it will, they will read actually the addresses written on the envelope, make sure that they are the right ones. If they are the right ones, then they will discard the outer envelope and just give the inner envelope that contains the names of the employees as well as the letter itself to the secretary in the floor above. Okay. Now, back to building 1. After the person in the postal department puts the letter in a new envelope that has the addresses of the buildings, we'll give it to someone in the lower floor that is responsible for actually mailing the letter. Okay. This could be simply a mailbox, okay, or it could be someone here that gives the letter by hand to a mailman. Regardless of the method, at the end of the day, the letter is injected into the postal system. Okay. Once it is inside the postal system, it gets transported, for example, by car and then by plane and then by car again. There is actually an entire trip until the letter goes to a mailman who will be responsible for delivering it to building 2. Either the mailman is going to put that letter in another mailbox, or they're going to give it to someone who works in building 2 by hand. Now the letter has actually arrived at the destination and it makes its way up to the top floor where the employees are. So in building 1, the letter is generated by someone, written by hand, given to the secretary, and then given to the postal department, then injected into the mail system. And then in building 2, it is received by someone or put in the mailbox, sent to the post department, sent to the secretary, and up to the employees. In each one of these levels, or we can call them now layers, there is a certain functionality. The employees write the letters, they actually generate the data. They give it to the secretary, whose job is to give the right letter to the right employee in building 1 and in building 2, using data that they exchange with each other. So, for example, the secretary in building 1 may actually not just write the name of the employee, they may write also their email, or they may write, for example, their ID in the company. This data will be understood by the secretary in building 2. Okay, so it's as if the secretary in building 1 is communicating virtually with the secretary in building 2. I'm saying virtually because it's not direct communication. They're communicating using the data that they are writing on the letter. In the postal department, someone actually writes the addresses of the buildings, building 1 and building 2, so that the postal system can understand how the letter will be forwarded until the letter reaches building 2. And then someone in the postal department in building 2 will read this address and make sure that the letter is actually intended to someone in building 2. And then they don't care about which person is going to receive this letter because it's not their job. They're just going to give the letter to the secretary in an above floor, and this secretary is going to sort out who is going to actually receive this letter. It's a layered system. Each part or each layer has a functionality, and they do this functionality in a certain way. For example, the layer where we have the secretary, you could actually fire the secretary and hire a new one who works in a different way, and the entire system will remain intact. For example, let's say the first secretary only collects letters from employees once every 3 days. If you fire the secretary and hire a new one who collects letters from employees once every day, the entire system is left intact. There are no other changes. You don't have to change anything in the postal system or the post department or anything else. Even the employees who write the letters, they don't actually have to do anything else. So the layered system serves to make the entire system modular, meaning that you can actually change functionalities in a certain layer without affecting the entire system overall. So how is this similar to what we have in the internet? In the internet, our top layer is actually called the application layer. This is where our data is generated. And in the application layer, we have application layer protocols. An example of an application layer protocol is HTTP. Regardless of what the protocol is, because actually we have many application layer protocols, there are protocols related to email, there are protocols related to WhatsApp or Skype, there are many application layer protocols. This application layer protocol defines how the content is generated. For example, in our analogy, the employees may have to write the letter in a certain way. For example, they have to write the date on the top and they have to write the title of the letter, and then they have to say, for example, dear sir or whatever, and they have to sign in the end. This would be a format. And if it is a strict format, then an employee in building 2 should not accept the letter unless it is written in this format. In the internet, an application layer protocol defines such a format for every message, meaning that the message has to be written in a certain format such that the application layer protocol in the receiver can understand it. And obviously, it should be the same protocol running in building 1 and building 2, or device 1 and device 2. If you're talking about HTTP, then the message generated by the HTTP protocol in the first device will be understood by the HTTP protocol running in the second device. Okay. So the top level or the top layer is analogous to the application layer. The layer below it, which we said has something called the secretary, is called the transport layer. The transport layer, and there is a transport layer at both devices. The job of the transport layer is to accept the data that has been generated by the application layer and deliver it to the right process at the destination. In your computer, you are typically running many applications at the same time, and all these applications may actually be communicating on the internet. For example, you have Facebook running, you have WhatsApp, you have a web browsing application, for example, and all of these are sending and receiving data at the same time to and from the internet. Okay, so when the response comes back, whose job it is to say this data is coming to which application? For example, you open a Facebook tab on your web browser and you want to load your Facebook page. So this Facebook data is coming from a server. Once it comes back from the Facebook server, how does your device know that it is actually Facebook data and I'm going to give it to the tab that is running Facebook? Okay, this is actually the job of the transport layer. And the transport layer does its job based on a type of address that is called port numbers. Basically, when the application layer opens a process, okay, this process will be given an ID by the transport layer. This ID is called a port number. Okay. And then the receiving end will also have a process that is going to accept the data. This process will also have a different port number. So the transport layer at the sender will insert two port numbers to each application layer data. The first port number is called the source port number, and the one belonging to the receiver is called the destination port number. So that when the packet arrives at device 2, the transport layer can read the destination port number that has been inserted by the transport layer in device 1 and can understand which process in the application layer will receive this data. Okay, so it's as if the transport layer at the sender is communicating with the transport layer at the receiver using the addresses which are port numbers. The sender is telling the receiver which process at the sender generated the data and which process at the receiver should actually receive the data. Never mind now how these port numbers are chosen. We will discuss them when we discuss the transport layer. But for now, we know that the data is generated by the application layer and the transport layer adds to it port numbers. By the way, when we say the transport layer adds to it port numbers, it is added actually in something called a header. So if this is the message that is generated by the application layer, the transport layer will add a transport layer header. And this header is just a piece of data that will include some information related to the transport layer. That's something we're going to discuss later in the course. And among this information will be the port numbers. So the port numbers are actually our first type of address that we will discuss. So in our analogy, when we were discussing building 1 and building 2, we said that below the secretary, we have the postal department. In the internet, the postal department is called the network layer. The network layer is responsible for transporting the data across the internet. It does that based on a type of address that we are mostly familiar with, which is called the IP address. So in our example of the buildings, we said that the postal department will add the address of building 1 and the address of building 2. Okay. In the internet, the network layer will add the IP address of the source, which is the sender, and the IP address of the destination, which is the final receiver, the one where the data is supposed to end up. Okay. And again, never mind where the source and destination IP addresses come from. We'll discuss it later. For now, assume that the network layer knows somehow the source and destination IP address and it inserts them in the packet. So after the transport layer header, there is also a network layer header that includes source and destination IP address. Now, how are the IP addresses formed? We said that every protocol in any layer defines the format at which the data will be inserted. So the application layer defines the format of an HTTP message. The transport layer defines the format of a port number. The network layer will define the format of an IP address. Okay. Just as when you write the address of a building in building 1 or building 2, the address that you write must actually have a specific format. For example, you write the building number, and then the street name, and then the city, and then the country, and then you have the postal code. It's a fixed format. Without actually having this fixed format, the mailman would not be able to understand the address and will not be able to deliver the letter. As long as you write the address in this understandable format, the mailman and the postal system in general will actually be able to understand this information. And we have actually reached the first layer that communicates with the internet in general, not just within a device, because the IP addresses will be needed by the internet to deliver the data to the destination. Okay, the routers in the internet, or more accurately in the internet core, will need the source and destination IP addresses to be able to deliver the packet of data to the destination device. Okay. As long as the devices use the standard format IP address, the routers will be able to understand this format and will be able to deliver the packet. Now, below the network layer, we have something called the data link layer. The data link layer is responsible for communication over a single hop. For example, how will building A, or how will an employee in building A deliver the letter to the mailman? Are they going to give it by hand? Going to put it in a mailbox? Are they going to take their bicycle or their car and drive all the way to the nearest post office and give the letter to them? Regardless of the method, this would be equivalent to a data link layer. The analogous example in the internet would be when you access the internet at home. How are you accessing it? This is actually the first hop. This is the first place where your data packet is going to be transported. Are you connected using a wired cable to your router, an Ethernet cable, for example, or are you using Wi-Fi, or are you using your mobile and sending the data via a mobile network? Each of these types of systems will have its own data link layer that is responsible for sending the data across one hop. So if you are actually using Wi-Fi, then there is something called the Wi-Fi protocol that is responsible for taking a packet from your device, transmitting it wirelessly, and receiving it at your Wi-Fi router. Once it reaches the Wi-Fi router, it gets transported to another router. And the first router is connected to the second router using a particular medium. It could be, for example, fiber optics cable or something like that. So there is another data link layer protocol that is responsible for moving the packet from the first router to the second router, and then from the second to the third, and third to the fourth, and so on until the packet reaches the final destination. So if this is you're sending a packet. This is, for example, your device, and you're sending a packet to the first router. This here, there is a particular data link layer protocol that governs how the data is transported to the first router. And then from the first router to the second, there is, so this is DLL1. There is another data link layer protocol, could be the same, could be different. Another data link layer protocol that is responsible for transporting the packet from router 1 to 3 to 2, and then 2 to 3 until it reaches the destination. So in our example of the buildings, let's say you give the packet by hand, give the letter by hand to the mailman. This is actually the first data link layer protocol. The mailman, maybe he's on a bicycle or he has a motorcycle or something like that, and then they drive or they ride their bicycle to or back to the postal office. Okay? This is another data link layer protocol. First hop, you actually give the letter by hand. So there is a protocol governing that. And then in the second hop, the mailman drives to the postal office. So he has to, for example, to follow the traffic rules. He has to stop at traffic lights. He has to give traffic signs, things like that. Once the packet reaches the post office, let's say it is packaged into boxes and then taken to the airport by car or by truck. Okay, then there is another set of protocols to be followed there. Once it's in a plane, there is a different set of protocols that govern how the plane travels. Okay, so at every hop, there is a data link layer protocol that defines how the data travels over this particular hop. The final layer below the data link layer is called the physical layer. And the physical layer, so here is also there is a data link layer, and the final layer is called the physical layer. The physical layer is responsible for communication across a medium. Basically, the physical layer is responsible for the hardware. It's responsible for converting the ones and zeros to electrical signals at the sender and converting the electrical signals back to ones and zeros at the receiver. So that starting from the data link layer, we're only talking about ones and zeros. We're not talking about electrical signals anymore. These are actually our 5 layers. There is one type of address that we didn't discuss, which is a type of address that is available at the data link layer, which is called the MAC address, sometimes also called the physical address. So the data link layer will also add another header that includes the source and destination MAC address. The MAC address, as we said, is a physical address that it is used to identify the device itself. So now we can actually look at the differences between all the types of addresses that we have and why do we have all these addresses. The port numbers at the transport layer identify the process within a device, meaning that if you have several applications running, it is the job of the port number to identify which application will actually consume this data. Okay, so the port numbers identify the application or the process. The IP address identifies the device itself. So it's analogous to the address of the building. So the IP address identify the device itself. That means your device has an IP address. The applications within your device will have port numbers. So the combination of IP address plus port number identify the device and the application within that device. Both of them are important because if you want to send a packet to an application in a different device, which is exactly what you want to do, you have to know the IP address of the device so that the packet makes it to the device, and then you have to have the port number so that the packet makes it to the right process within that device. So what is then the use of a MAC address? The port number is determined by the device itself. That means the device gives a port number to the processes that it's running. The IP address is given by the network. The network actually assigns you an IP address, and when you log off the network, the IP address is taken from you. The MAC address is a physical address. It's a property of the device. Your MAC address comes with your device, whatever it is, and no one can actually take it from you. It's a property of the hardware itself. No one gives it from you. It's permanent. No one can actually take it from you. IP addresses are dynamic. Port numbers are dynamic. MAC addresses are permanent and static. Okay. So what is the use of a MAC address if we already have an identifier for the device? Basically, in many types of networks, all the communication are done based on MAC addresses. These are primarily local area networks. So if you have, for example, a Wi-Fi hotspot, and this Wi-Fi hotspot is covering or is providing a service to several devices. Even though these devices will all have IP addresses, the Wi-Fi access point or the Wi-Fi router itself will be communicating with these devices or identifying these devices based on MAC addresses. Okay. So in local area networks, for example, networks that are based on switches, and we will see an example in a little bit, or networks that are based on Wi-Fi or something like that, it could be that the MAC address is the one that is used for forwarding and receiving data. Okay. In any case, the MAC address is important to identify the hardware itself, to identify the device itself. This is why the MAC address has some privacy concerns. That means it has to be protected. If there is an application or a system that hijacks your MAC address, that means that they can identify your physical device. So it's something that can be kept protected. Okay. These are actually the layers, and the layers actually make up the protocol stack. Each layer communicates with its counterpart at the destination. So the application layer generates data that is understood by the application layer at the receiver. The transport layer generates a transport layer header that includes the port numbers, and these port numbers are read by the transport layer at the receiver. The network layer generates IP addresses, and these IP addresses are understood by the postal system or the internet core, and also understood by the network layer at the receiver. The data link layer generates a data link layer header that includes a MAC address, and this is understood by each and every hop. So if you have the example that I showed you here, you have someone sending data across actually several hops. The application in your device will generate the data, and the transport layer will add the transport layer numbers. The network layer will add the IP addresses. The IP addresses that are added are actually the source IP address of the device itself and the destination IP address of the final destination. So when the network layer adds the new network layer header, the source IP address is that of the first source, and the destination IP address is that of the first destination. As the packet jumps over the routers will not change the source or destination IP addresses in the packets. They will keep them as they are until the packet reaches the destination. The data link layer, on the other hand, at the source device, will include the source MAC of the device itself and the destination MAC of the first hop, that means of the first router. When the first router receives the packet, it is going to remove the data link layer header, and it will add a new data link layer header that includes its own source MAC and the destination MAC of the second router. Second router will do the same, will remove the data link layer header and will add a new one that includes its own source MAC and the destination MAC of the third router. Third router, when it sends the packet, it will have a new data link layer header that includes its own source MAC and the destination MAC of the final server. Because the MAC addresses and the data link layer are only serving local networks, the MAC addresses keep getting changed every hop. The IP addresses and the port numbers are fixed. They never change from source to final destination. However, the MAC address changes in every hop because the MAC address is a property of the local network. That means the MAC address is meaningless outside of a local network. It's not used for forwarding. You cannot actually infer from it anything. Okay. So why do we have this layered structure? As we said, it makes maintenance easier. So if you want to update, for example, the IP protocol, so up to the late 90s and early 2000s, the only IP protocol that was running was IP version 4. And then they proposed IP version 6. So in order to replace IP version 4 with IP version 6, and by the way, this process is not finalized yet, so we still actually have both versions running, you do not have to disrupt anything else in the system. You don't have to change anything about the transport layer. You don't have to change anything about the data link layer or the application layer or the physical layer. You can keep everything the same, and you just change the network layer protocols. So it makes maintenance easier. It makes updating the systems easier. And this here shows you actually our protocol stack. And it is the protocol stack that we have in the internet. And we see now the functionality that we have discussed in the previous example. The application supports the network application, so the application layer protocols such as HTTP, SMTP, that's the one for email, and FTP is the file transfer protocol. In the transport layer, the layer supports process-to-process data transfer. That means transferring data from one process in one device to another process in a different device. And there are only or mainly two transport layer protocols running in the internet. There are TCP and UDP. Since 7 or 8 years ago, there has been a lot of research into transport layer protocols, and there are new ones that are proposed, such as there is one called QUIC, for example. Okay. These are advanced ones that we're not going to discuss in the course. They are part of actually the elective course, Selected Topics in Modern Networks in the 9th semester. If you're interested, you can actually read about them. But the two main protocols that are used in the internet are TCP and UDP. The network layer is responsible for routing, is responsible for figuring out a path from source to destination, and is also responsible for adding the IP address. So we have the IP protocol, okay, which we have the versions IP version 4 and IP version 6, and we have routing protocols as well. Routing protocols are the ones that figure out the path from source to destination. Okay, similar to what your GPS does. So when you enter a destination in the GPS, there is a protocol that is very similar to routing protocols in the internet, whose job is to figure out what is the best route from source to destination. The data link layer or the link layer protocols, they are responsible for data transfer between neighboring network elements, so between one device and the other. And there are several protocols there. There is a TPP, which is typically found between routers. You have the internet and you have Wi-Fi. There are many different types of protocols found in the data link layer. And then finally, the physical layer is the bits on the wire, the transforming ones and zeros to electrical signals and transforming the electrical signals back to ones and zeros in the destination. So, which devices implement which layers? Okay. First of all, there is one golden rule. If you implement a layer in the device, you have to implement all the layers below it. That means you cannot have just the link layer. If you implement the link layer, you must implement below the physical layer. If you implement the network layer, you must have below it link and physical. If you implement transport, you must have network, link, and physical below it. And if you implement application layers, that means you have to implement the entire protocol stack. So when you have a layer in a device, you must implement all the layers below it. So in our discussion of the network or the internet structure, we said that the internet is roughly divided into core and edge. And the edge has our devices, the edge devices and the servers, okay? And the core has high-speed routers and switches. So what do these devices actually implement? If you think about the edge, as we said, is where our applications run. The routers in the core do not run applications. For example, a router will have no need to run WhatsApp, even if it is actually care about the content. The router doesn't even read the content. The only thing that the router reads is actually the network layer header, which has the IP addresses. And based on the IP addresses, it will figure out how to forward the packet to another router or to the destination. Okay, so the core doesn't actually need to run applications. So it doesn't need to implement an application layer. And because the transport layer is responsible for data transfer between application processes, if you don't have an application layer, then you have no need for a transport layer as well. And so the routers only implement network, link, and physical layers. Okay. The routers implement only these three layers. Whereas the edge, this is where our applications run. And so edge devices have to implement an application layer because this is where we find the applications. This is where the application data is generated. And as we said, if you implement an application layer, you implement the entire protocol stack. So the protocol stack is implemented in full at the edge, okay, in the edge devices, in our devices, and in the servers as well, while the switching devices, such as routers, implement only the bottom three layers, network, link, and physical. Switches are also a type of switching devices, so their job is only to do forwarding, but they only do forwarding in local networks. And as we said, in local networks, you can actually do forwarding based only on MAC addresses. So switches will only implement the bottom two layers, link and physical, because in the data link layer, this is where you find the MAC addresses. And so it's enough for a switch to do forwarding based on MAC addresses because it doesn't actually need an IP address to do forwarding because it's only supporting a local network. Okay. This is the protocol stack that we have in the internet, and this is going to be what we are going to follow in the course. So for the remainder of the course, we are going to take each layer and we're going to open it up and see what kind of protocols we have in it. For example, in the application layer, we will study HTTP and DNS, two types of protocols that are of high importance. In the transport layer, we will look at both TCP and UDP. In the network layer, we will look at the IP protocol and we will see different routing protocols as well. In the data link layer, we will take a look at a protocol such as ARP, the Address Resolution Protocol, and we will see the structure of MAC addresses as well. We will not really go into the physical layer because this is the job of communication students. We will just know that the physical layer transforms bits to electrical signals and electrical signals back to bits. In the past, there used to be another reference model that is called the OSI reference model, Open Systems Interconnection. It is very similar to the reference model of the internet. That means it has similar layers, except for two additional ones, which are presentation layer and the session layer. The session layer allows two devices to establish a session between them. That means they can synchronize what they send and receive. They can do something like checkpointing, providing, for example, a checkpoint at every bulk of data that is sent. Can do actually different jobs related to a particular session between a sender and the receiver. And the presentation layer basically defines the format. How is the data presented to the application? Now, why is it that these two layers were removed in the Internet Protocol stack? Because more or less they are a part of the application layer. So in the Internet Protocol stack, when we say application layer, it is actually understood that this application layer or the application layer protocols within will include actually the functionality of presentation and session if they are needed. Okay. Right. So final thing we will discuss is that we will take an example just to actually see how these layers are interacting or performing in practice. Now, let's say we have this network. We have a source device that is generating a message and wishes to send it to a destination device. The source device is connected to a switch, and the switch is connected to a router, and then the router is connected to the destination device. So because the source and destination are the ones who are running the application, they implement the entire protocol stack, as you see here. The router implements only the bottom three layers because it does forwarding based on IP addresses. The switch implements only the bottom two layers because it does forwarding based on MAC addresses. So how does this all work? At the source, the application generates a message, M, as you see here. Generated, the application layer gives it to the transport layer. And the transport layer will add the transport layer header. And as we know, the transport layer header has our first type of addresses, which are the port numbers. So at the transport layer of the source and destination port numbers are going to be inserted in the transport layer header. The source port number is the one that identifies the application layer process, and the destination port number is going to identify the destination process. Okay. Once the transport layer is added, the entire thing is then given to the network layer, which adds the network layer header. And the network layer header will have the IP addresses, source and destination IP address. And again, forget for now about how the source and destination IP addresses are discovered. Okay. Now, once the network layer adds the network layer header, including the IP addresses, it will give the whole thing to the link layer, which will add a data link layer header that includes the MAC addresses. So the network layer adds source and destination IP address. The source IP address is that of the source, and the destination IP address is that of the final destination. On the other hand, the data link layer will add the MAC address of the source, and the destination MAC address will be the MAC address of the switch. Okay, because the data link layer defines only what is happening over a single hop. So when the source generates a packet, the next hop will be the switch, meaning that it's going to send this packet to the switch, and the packet will contain the message and all the headers. Okay, and so in order for the switch to know that this packet is actually intended to it, it must have the destination MAC of the switch. So the data link layer at the source will generate the data link layer header, which include the source MAC of the source and the destination MAC of the switch. Again, forget for now how these addresses will be discovered. There is a mechanism that we will discuss later in the course. Now, once the MAC address generates and adds the data link layer header, it will then give it to the physical layer. And the physical layer will take all of these ones and zeros corresponding to the message and all the headers, and will actually transform all these ones and zeros to electrical signals and send them over the physical medium that is connecting the source to the switch. It could be, for example, a wireless connection, or it could be an actual cable connecting the source device to the switch. Regardless of the method, the physical layer will convert the ones and zeros to electrical signals, and these electrical signals will be received by the physical layer in the switch. The physical layer in the switch will transform the electrical signals back to ones and zeros and send them all to the data link layer. So what does the data link layer in the switch receive? It receives actually the message that was generated by the source, along with all the headers that have been also generated by the source: transport layer header, network layer header, and data link layer header. The switch, as you see, only has a link layer. So all these headers are meaningless for the switch, except for only one header, which is the data link layer header. And this is exactly what the switch focuses on, and this is exactly what the switch reads. The switch actually doesn't read all the other headers. This is why it is the outer header, the data link layer header. The switch will look for this header. It will read the information within. In particular, it will look for the source and destination MAC address. It will learn that the source MAC address is that of the source and destination MAC is that of the switch. And now it knows that it should actually forward, sorry, this is wrong. The destination MAC in this case, the one that is added by the source, will actually be the MAC of the router, not the switch. The switch is actually a transparent device. Okay, in a local network, a switch does nothing but forwarding. You cannot actually send something to the switch. The switch is a transparent device that only does forwarding. So in the data link layer, the switch will actually add the source MAC of the source, and the destination MAC will be that of the router. And so when the switch receives this data link layer header, it will read the source MAC of the source and destination MAC of the router, and then it will actually remove, it will forward this packet to the router. That means it will give the packet back to the physical layer, and the physical layer will transform the ones and zeros, which corresponds to the message plus all the headers that have been generated by the source, to electrical signals and send them to the router. And the physical layer of the router will receive this packet. Okay. So again, the data link layer header at the source includes the source MAC of the source and destination MAC of the router, which the switch is going to use to forward the packet to the router. Once the packet is received at the router, okay, so you see here the packet is now at the physical layer of the router, transforms it back to ones and zeros, and gives it to the data link layer at the router. Again, the data link layer at the router will read the data link layer header. It will learn that the packet is indeed intended to the router because it includes the destination MAC of the router. And so the data link layer will remove the data link layer header and will give the remaining packet to the network layer of the router. Now the network layer of the router, you see we had to remove the data link layer header because the network layer will not understand it. It has a different protocol. It will only understand network layer protocols. And so the network layer at the router will read the network layer header that has been inserted by the source, which includes the IP addresses of the source and destination. And based on this information, the network layer in the router will know how to forward the packet. And so it now knows that it needs to forward the packet to the destination because it reads the destination MAC address. So it gives the packet back to the link layer at the router. So now it needs to forward it. So it gives it to the link layer of the router, which adds a new data link layer header. This new data link layer header will include actually the source MAC of the router and the destination MAC of the final destination, because this is actually the next hop. And then the network layer header, the transport layer header, and the message will be left unchanged. That means they are the same as the one that has been generated by the source. This whole thing is now given to the physical layer, which transforms it to electrical signals and sends it on its way to the destination to be received by the physical layer at the destination. Gives it to the data link layer header, which reads the data link layer header and removes it after confirming that the destination MAC is intended for it. Network layer will read the network layer header and remove it after confirming that the destination IP address is correct. The transport layer will read the transport layer header and find the port numbers and knows from the port numbers which application layer process is supposed to receive the packet. This is the one that has actually the destination port number in the message itself, and will remove the transport layer header and give only the message to the right process at the destination. This is basically how a packet makes its way all the way from source to destination. The idea of having a message as well as headers is called encapsulation. That means you take the message M, you encapsulate it in a header, and then you take the message and the header and you encapsulate it in another header and another header until it reaches the physical layer. In each layer, the protocols will read only the headers that are intended for them. That means the transport layer will never actually read the network layer header, and the network layer will never read a data link layer header or a transport layer header. Each layer will read only the headers that are intended for them. Okay, that's it for this lecture. The idea or the topic of the protocol stack is very important. I recommend that you watch this video several times until you understand it well. It is essential for understanding all the topics for the remainder of the course. And with that, I wish you luck and we'll talk to you next time.